Hello, welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we had seen how OFDM converts the frequency selective fading channel into a frequency flat channel across each subcarrier. Hence, the net system model is given as Y0 equals H0 times X0, where Y0 is the received symbol across the 0th subcarrier, H0 is the channel coefficient corresponding to the 0th subcarrier, X0 is the symbol loaded onto the 0th subcarrier. Similarly, Y1 equals H1 times X1, so on and so forth. In general, Yk equals Hk times Xk across the kth subcarrier, and so on we have until Yn minus 1 equals Hn minus 1 times Xn minus 1, that is a total of n subcarriers. And we said thus this essentially converts a wide band channel of bandwidth B into n parallel narrow band channels of bandwidth B by n, such that there is no inter-symbol interference across any narrow band channel and detection is easy across each narrow band channel. That is the big advantage of this OFDM system. And we also said that the system architecture or the system schematic is now modified to with the addition of the cyclic prefix block. That is, we need to take a prefix, that is, we need to prefix a string of symbols in front of the OFDM symbol to avoid inter OFDM symbol interference, and at the receiver we remove the outputs corresponding to this cyclic prefix, and we also add a block for the detection of the symbols corresponding to the each subcarrier before multiplexing them onto or converting them from parallel to serial and passing this data onto the higher layers. Okay. And also we said that this cyclic prefix is slightly tricky in the sense that when you add a cyclic prefix, since you are repeating symbols, they do not carry any additional information. Hence, adding a cyclic prefix results in a loss of the effective information rate, but we said we can compensate for that by increasing the OFDM number of subcarriers, so the block length. As the number of subcarriers increases, we had seen that this loss in spectral efficiency tends progressively to 0, and what this means also is essentially that as you are adding, as you are increasing the number of subcarriers, the OFDM symbol time is progressively increasing, so that the effect of inter OFDM symbol interference is now restricted to a smaller and smaller fraction of the OFDM symbol. That is what it means to increase the number of subcarriers. And we also said that this essentially means that the bandwidth of each subcarrier, that is B over n, is much smaller than the coherence bandwidth, thus ensuring frequency flat fading across each subcarrier. That is the essential idea behind this OFDM system. And finally, we started to look at an example of an OFDM system. We considered a 4G WiMAX scenario. We said WiMAX is the 4G standard, it is a 4th generation wireless communication standard, and we started looking at a fixed profile, that is, WiMAX has several profiles. We started looking at one of the profiles, which is a fixed profile of the WiMAX standard. So, let us continue with that example. So, continuing with that example, we said that the WiMAX fixed profile of WiMAX, the WiMAX we said we considering WiMAX, the fixed profile. WiMAX is a 4G mobile, WiMAX is in general a 4G wireless communication standard. It is a 4G wireless communication standard. Okay. And this profile, this fixed profile of WiMAX has n equals 256 subcarriers, and we also said that the bandwidth per subcarrier, that is Bs, is 15.625 kilohertz. So, Bs, which is nothing but B over n, equals 15.625 kilohertz. So, Bs, the bandwidth per subcarrier is 15.625 kilohertz. Now you can see this 15.625 kilohertz is much less than the coherence bandwidth of the system, which is around 200 to 300 kilohertz. Hence, we can safely say that each subcarrier experiences frequency flat fading. Okay. So, we notice that Bs equals, so notice Bs equals 15.625 kilohertz, which is much smaller than the coherence bandwidth, which is approximately 300 kilohertz. So, this is much smaller than the coherence bandwidth, which is approximately around 200 to 300 kilohertz. Hence, we can safely say that in this fixed profile, each subcarrier experiences frequency flat fading. Hence, each subcarrier indeed experiences frequency, hence each subcarrier indeed experiences frequency flat fading, because the bandwidth per subcarrier is much less than the coherence bandwidth. Now, what is the bandwidth of the system? What is the total bandwidth of the system? We know that the total bandwidth of the system is nothing but the bandwidth per subcarrier into the number of subcarriers. So, we have B by N equals 15.625 kilohertz, which means B is equal to N times 15.625 kilohertz, which is essentially equal to, we said N equals 256 subcarriers, hence this is 256 into 15.625 kilohertz. This is nothing but 4 megahertz. Hence, the bandwidth of this fixed profile OFDMA is B equals 4 megahertz. Hence, you can see this bandwidth is 4 megahertz, which is a wideband channel. It is much larger than the coherence bandwidth of 300 kilohertz. By dividing this into n subcarriers, 256 subcarriers of bandwidth 15.625 kilohertz each, this system is ensuring that each subcarrier experiences only flat fading and not frequency selective fading. Okay. Thus, the total bandwidth B is 4 megahertz. And now, let us compute some other parameters. What is the OFDM symbol time without the cyclic, that is before you add the cyclic prefix? What is the OFDM symbol time? So, OFDM symbol time without cyclic prefix, that is without cyclic prefix, is nothing but N over B. So, OFDM symbol time without cyclic prefix is N over B, which is essentially equal to 256, which is essentially equal to 256 divided by 4 megahertz, which is 4 into 10 to the power of 6 hertz. So, OFDM symbol time is 4 megahertz, 256 divided by 4 megahertz, which is nothing but 64 microseconds. So, this is nothing but 64 microsecond. So, this OFDM symbol time is basically 64 microseconds, but this, remember, comprises only of n samples, and this is before the addition of the cyclic prefix. Now, we said the cyclic prefix depends on what is the channel delay spread. The cyclic prefix has to be greater than the channel delay spread. So, the cyclic prefix in this OFDM symbol, the standard cyclic prefix cyclic prefix in WiMAX. In WiMAX, the standard cyclic prefix is 12.5% of symbol time, equals 12.5% of symbol time, which is essentially equal to 12.5 divided by 100 into 64 microseconds. That is essentially 12.5% is nothing but 1/8, which is essentially 8 microseconds. Hence, the duration of the cyclic prefix, this is nothing but duration of this is nothing but the duration of the cyclic prefix. What this says is, I have an OFDM symbol, in which there is 64 microseconds of actual symbol. This is the actual symbol, and there is 8 microseconds. This is the cyclic. This is the cyclic prefix. In fact, this 8 microsecond is drawn from the last 8 microseconds. So, last 8 microseconds of the OFDM symbol is taken from here, not removed, but simply copied and prefixed. So, it is not removed, it is simply copied and prefixed before the OFDM symbol. So, the net now becomes 64 plus 8 . 64 microseconds plus 8 microseconds equals 72 microseconds. Hence, net symbol duration, net OFDM symbol duration, that is the net, that is the total OFDM symbol duration with cyclic prefix equals 72 microseconds. The total OFDM symbol duration with cyclic prefix is now 72 microseconds. Now, what is the number of samples in this cyclic prefix? That can also be computed. Number of samples is nothing but, that is nothing but the duration of CP divided by sample time. So, that is nothing but CP duration divided by sample time. CP duration we saw is 8 microseconds, sample time is nothing but 1 over B, which is 4, B is 4 megahertz, hence this is nothing but 8 microseconds by 1 over B, which is 8 microseconds into B, which is 8 microseconds into 4 into 10 to the power of 6, which is nothing but 32. Hence, total number of samples in CP equals 32 samples. We know that the OFDM symbol without CP, cyclic prefix, contains 256 samples, that is the size of the IFFT. We add 32 samples of cyclic prefix. So, again drawing a similar figure. This is the 256 . This is the 256 sample OFDM symbol. What we are doing here is essentially we are adding 32 samples of cyclic prefix, and these are taken from this part. So, this is 32 samples and this is the cyclic prefix, and hence total number of samples with cyclic prefix in one OFDM symbol equals 256 plus 32 equals 256 plus 32 equals 288 samples. That is the total number of samples in this OFDM symbol with the cyclic prefix. Hence, the loss in spectral efficiency, the finally what we want to compute is the loss in spectral efficiency Why is there a loss in spectral efficiency? Remember, cyclic prefix itself conveys no information, hence all added cyclicity symbols constitute a loss in spectral efficiency. That is nothing but number of symbols in CP divided by total number of symbols, that is 288, which is also the same as the CP duration, that is 8 microseconds divided by the total OFDM symbol duration, that is 72 microseconds, which is essentially 11.1%. So, roughly 11.1% is lost because of addition of CP. So, this is essentially loss because of addition. So, this 11.1% is essentially the loss in the effective information rate of the system because of the addition of cyclic prefix, symbols in the cyclic prefix, which themselves convey no information. And as we saw, this loss can be progressively brought down by increasing the number of subcarriers. That is, if I have n equal to 56, 512, 1024 subcarriers, as the number of subcarriers keeps increasing, this loss in terms of throughput keeps progressively decreasing. Okay. Hence, that covers the basics of OFDM, which is we talked about what OFDM is, what is the motivation behind OFDM. We talked about, that is, we introduced the multi-carrier modulation system, and then we introduced what are the problems, implementational problems of this multi-carrier modulation, and how OFDM removes those problems, or how OFDM essentially makes the implementation of such a system easier by the introduction of an IFFT at the transmitter and FFT at the receiver. And also we demonstrated the use of the cyclic prefix and how the use of the cyclic prefix removes the effects of inter OFDM symbol interference. All right. So, we have so this essentially completes an introduction to the OFDM. Now, we want to look at some other extensions to an OFDM system. For instance, now what we want to start looking at is, we have looked previously at a MIMO system, that is a multiple input, multiple output wireless communication system. Now, what we want to look at is, we want to also look at how can MIMO be coupled with OFDM, that is, how can we have a MIMO-OFDM system, that is both working together in a communication system. So, we want to look at the next topic we want to look at is MIMO-OFDM, where MIMO, as we already know, stands for multiple input multiple output wireless systems, and OFDM, just to remind you, stands for orthogonal frequency division So, we know that MIMO stands for multiple input, multiple output wireless communication system. It is nothing but having multiple antennas at the transmitter, multiple antennas at the receiver. Then we also have OFDM, which is orthogonal frequency division multiplexing, which converts a frequency selective channel into a set of parallel flat fading channels. So, now we want to combine these two technologies to achieve a much higher throughput and much easier receive processing at the receiver. Alright, so the motivation behind MIMO is to achieve a higher throughput. The motivation behind OFDM is to convert frequency selective into flat fading set of parallel flat fading channels. So, we couple MIMO and OFDM to achieve both of them, that is high throughput as well as simplified processing at the receiver, that is converting the frequency selective fading channel into a set of parallel flat fading channels. So, hence Let me write it down. MIMO-OFDM is a combination of MIMO with OFDM, is a combination MIMO-OFDM is a combination of MIMO, which is multiple input, multiple output, it is a combination of MIMO, which is multiple input, multiple output communication, with OFDM. OFDM, which stands for orthogonal frequency division multiplexing. So, MIMO-OFDM, the definition is essentially it is a combination of MIMO, which is multiple input, multiple output communication, with OFDM, which stands for orthogonal frequency division multiplexing. Okay. And as we already said, OFDM converts a frequency selective channel into a set of parallel flat fading channels. MIMO-OFDM converts a MIMO frequency selective channel into a set of parallel flat fading MIMO channels. All right. So, in MIMO-OFDM, with the time domain channel is a MIMO frequency selective channel, and MIMO-OFDM converts this MIMO frequency selective channel into a set of parallel flat fading MIMO channels. All right. So, similar to OFDM, MIMO-OFDM converts its frequency selective MIMO channel into multiple parallel flat fading channels, into multiple parallel flat fading the key here is flat fading MIMO channel. So, it converts a MIMO frequency selective channel into a set of parallel flat fading MIMO channels, thus simplifying receiver processing. All right. Now, in the absence of a flat fading MIMO channel, one needs to eliminate MIMO intersymbol interference, and this essentially implies that you need a MIMO equalizer. All right. So, what MIMO-OFDM does is that it removes the need, or it essentially simplifies the receiver processing by converting this into a set of flat fading MIMO channels, thus making it unnecessary to have to implement a MIMO equalizer, which is much complicated. Hence, MIMO-OFDM significantly simplifies baseband MIMO receiver processing. It simplifies baseband receiver processing by eliminating the need for a complex MIMO equalizer. it simplifies baseband processing by eliminating the need for a complex MIMO equalizer. That is, this MIMO this MIMO frequency selective fading channel in fact causes MIMO intersymbol interference. Hence, in the presence of MIMO intersymbol interference, one needs a MIMO equalizer. Thus, by removing the need for a MIMO equalizer, this significantly simplifies baseband receive processing. That is, it eliminates MIMO intersymbol interference. Alright. So, that is the essential advantage of MIMO-OFDM. Now, of course, to understand it, first we have to understand how does a MIMO frequency selective channel look. We have to understand, we have to get an in-depth understanding of what is the nature of MIMO frequency selective channel which causes MIMO intersymbol interference. So, first what we are going to start with is we are going to start with an introduction to the MIMO frequency selective communication channel model. Okay. So, I am going to start with the frequency selective MIMO channel. Now, remember the frequency selective channel, a single input single output channel, is modeled as follows. To let me remind you that a frequency selective CISO channel is modeled as an FIR filter. It is modeled as an FIR remember the frequency selective CISO channel is modeled as an FIR filter. In fact, the output is given, the system model is given as YK equals summation L equals 0 to L minus 1 H of L x k minus L plus n k, which essentially translates to, if you look at YK, this means YK equals H 0 x k plus H 1 x k minus 1 plus so on plus n k, and this we said each output symbol depends on both the current symbol and also the past symbols x k minus 1. These are the past symbols x k minus 1, x k minus 2 and so on. So, the current symbol output y k depends on both x k, which is the current symbol, and also the past symbols, which essentially means that there is intersymbol interference. So, this essentially means that there is intersymbol Okay. So, this essentially means that there is intersymbol interference in this channel tap, which is modeled as an FIR filter. Hence, now how do we model a MIMO frequency selective channel? The natural answer is a MIMO frequency selective channel is modeled as a MIMO FIR filter, where each channel tap is a MIMO channel matrix. Hence, a MIMO, hence the first result that we want to present, hence a MIMO frequency selective channel is or can be modeled as a MIMO FIR filter. Hence, a MIMO frequency selective channel can essentially be modeled as a MIMO FIR filter. What does this mean? So, if I look at the received symbol vector at the MIMO receiver, remember we said in a MIMO system you have multiple transmit antennas, multiple receive antennas. Hence, the transmitted symbol is nothing but it is a vector comprising of the transmitted symbols at each receive antenna, and the received symbol is also a vector corresponding to the received symbols at all the receive antennas. Hence, the system model, hence we have the receive vector now yk bar y bar k equals summation L equals 0 to capital L minus 1 h of L x bar of k minus L plus n bar of k, where y bar k is the received r cross 1 symbol vector, this is the received r cross 1 symbol vector, this is the transmitted k cross 1, this is the transmitted k cross 1 symbol vector, and hk is the channel matrix. Now, remember this is the Lth tap, but this is the channel matrix corresponding to the Lth tap. Remember this is HL is nothing but the Lth tap, but in this MIMO frequency selective channel it is a matrix. So, this is the channel matrix corresponding to Lth tap. In fact, HL is an R cross T matrix. In fact, HL is an R cross T matrix, and n bar is nothing but, this is nothing but the R cross 1 noise vector. This is nothing but the R cross 1 received noise vector, that is n bar k. This is the MIMO frequency selective channel. In fact, we can write this explicitly. So, writing this explicitly, we can see that this is nothing but y bar k equals h0 x bar k plus h1 x bar k plus k minus 1 plus h2 x bar k minus 2 plus HL minus 1 x bar k minus L plus 1 plus n bar of k, and this x bar of k is nothing but the transmit vector at time t. So, x bar of k is transmit vector at time t. X bar k minus 1 is vector at time t minus 1, this is transmit t minus 1, x bar k minus L plus 1 is transmit and x bar s t minus is transmit vector at time k minus L plus 1, this is the transmit vector. Hence, y bar k depends not only on x bar k, but it depends on x bar k minus 1, x bar k minus 2, so on up to x bar k minus L plus 1. Thus, this is a model of, and remember this is a model of inter-symbol interference, but it is inter-vector symbol interference. Hence, this is a frequency selective MIMO channel. All right. So, each of these, so y bar k depends on the transmit vectors x bar k minus 1, so on up to x bar k minus L plus 1. Hence, it depends on the transmit vectors x bar k minus 1, so on up to x bar k minus L minus 1, that is the previous transmit vectors. So, which are essentially the previous transmit symbol vectors. Hence, the above is, hence this channel is an L-tap frequency selective MIMO channel. Hence, these are the previous transmit vectors. Hence, this is an L-tap frequency selective hence this is the model of an L-tap frequency selective MIMO channel. Hence, there is ISI between the current and previous transmit symbol vectors, not the symbols, but between the vectors. Hence, in a MIMO frequency selective channel, ISI occurs between the current and previous transmitted symbol vectors, that is inter-symbol interference occurs between current and transmitted inter-symbol interference occurs between current and previous transmitted symbol vectors. Hence, for a MIMO-OFDM system, one needs to perform the IDFT or the IFFT operation at each transmit antenna. Remember, the symbols are now not simply one symbol, but there is one symbol transmitted from each transmit antenna. Hence, now the IFFT operation of OFDM has to be performed at each transmit antenna, that is, for the block of symbols at each transmit antenna, one has to perform an IFFT operation. Hence, in an MIMO-OFDM system, hence in a MIMO-OFDM system, one needs to perform the IDFT or IFFT operation at each that is, what all operations that we had in the OFDM schematic at the transmitter now have to be performed at each transmit antenna in this MIMO-OFDM system, that is, at each transmit antenna in this MIMO-OFDM system. Okay. Hence, let us look at a schematic. Let us look at the schematic of this MIMO-OFDM system. Let us look at the transmitter schematic. If I look at the transmitter schematic, I am going to have one serial to parallel block to demultiplex amongst the transmit antennas. So, this is a serial to parallel demux or demultiplexing for transmit. This is the serial to parallel demultiplexing for the transmit antennas. Then now I will, after demultiplexing on the transmit antennas, at each transmit antennas I will again demultiplex to form a block on which the FFT is performed. So, on each transmit antenna, first I will further demultiplex to form a block. So, this is S/P demux. I will have a block of symbols. On this block I will perform the endpoint FFT. So, in this block I perform the endpoint IFFT essentially. Once I perform the endpoint IFFT, I multiplex this again similar to what we have done before. I multiplex these into parallel to serial. I convert this from a parallel block to a serial block. Once I convert this from a parallel to serial block, I will add the cyclic prefix. Now, I will add the cyclic prefix, that is, at each transmit antenna I am adding the cyclic prefix. Finally, what I will do is I will transmit this from the transmit antenna. So, this is transmit antenna 1. I am going to transmit this from transmit antenna 2, but before that I have to do this processing before I can transmit this from transmit antenna 2. Similarly, at transmit antenna 2, I am going to do a serial to parallel demultiplexing operation. This is the serial to parallel demultiplexing or blocking operation at transmit antenna 2. Then I will do the endpoint FFT of the symbols for this is the endpoint IFFT for transmit antenna 2, followed by now take these IFFT samples and convert them from parallel to serial, that is multiplexing, and now add the cyclic prefix at the transmit antenna 2. So, this is addition of the cyclic prefix at transmit antenna 2. So, this is first one is transmit antenna 1, second one is transmit antenna 2, all right, and so on so forth. I have T transmit antennas at which I have to do all these operations. So, at the Tth transmit antenna, I again have a serial to parallel demultiplexing operation, followed by this I will again have a block of n symbols which are loaded onto the n sub KERAS, or which I have to do an IFFT at the Tth transmit antenna, followed by a block of followed by the endpoint IFFT at the Tth transmit antenna. Now, I have to again multiplex these. So, demultiplex these. So, I parallel to serial, I multiplex all of them into the same line. Before, of course, I add the cyclic prefix now at the Tth. So, addition of the cyclic prefix. So, I add the cyclic prefix now at the Tth transmit antenna and then at transmit, and this is the transmit antenna T. So, this is the Tth transmit antenna, and in fact these, if you look at these here, these are nothing but my multiple transmit antennas. These are nothing but the multiple transmit antennas, that is the front end, all right, that is the back end, that is the transmitter, all right. These are the multiple transmit antennas. Before the transmitting on each transmit antenna, I have to perform these OFDM operations, which is blocking, IFFT, then again deblocking, that is serializing, addition of CP, transmission. Okay. So, this has to be performed at each transmit antenna essentially, and before that I have to take all the available symbols and divide them amongst transmit antennas. So, let us say, let me consider a system with n equals 256, for instance. Let us say I have an example, n equals 256 subcarriers and T equals 4 transmit antennas. So, what I have here is I have a block of 124 symbols that are coming in. So, I have a block of 124 symbols that are coming in. Out of this I have to divide them into 4 transmit antennas. So, now I divide 256 symbols amongst each of the 4 transmit antennas. So, I get n times T symbols in, send a block of n symbols to each transmit antenna, perform IFFT, load them onto the subcarriers, all right, and then serialize them, add cyclic prefix, transmit from each transmit antenna. This is now the schematic of the MIMO-OFDM transmit schematic. So, let me write that down. This is now the MIMO-OFDM, this is now the MIMO-OFDM, this is the MIMO-OFDM transmit this is the MIMO-OFDM transmitter schematic, all right. This is the MIMO-OFDM transmitter schematic. How is transmission to be done, or the transmit pre-processing to be done in a MIMO-OFDM system, okay. And correspondingly, now we will look at what is the corresponding receive processing that has to be done in this MIMO-OFDM system. What is the corresponding receive processing that needs to be done at the receiver, similar to what we had in the OFDM receiver? I will have to remove the cyclic prefix. So, CP removal. So, I will have a block to remove the cyclic prefix, followed by I will have a block for serial to parallel conversion, serial to parallel, which is also nothing but a demux operation, all right. So, serial to parallel is nothing but a demux operation. So, demultiplex them, and now here what I will do is I will perform the endpoint, FFT, and after the FFT what I have to do is I have to do the detection. Similar to what we had in OFDM receiver. Remember, we said we have to do a detection, but this is not a simple detection, but this is a MIMO detection. Remember, we are dealing with a MIMO frequency selective channel, which is converted into MIMO flat fading channels. Hence, we have to perform a MIMO detection. I will come to that slightly later, but let me illustrate the processing at the rest of the receive antenna. Similarly, we have at the second receive antenna, we have again the removal of the cyclic prefix, that is the CP removal, followed by we have the serial to parallel demux, followed by we have the endpoint FFT. So, this is the first receive antenna, this is the second receive antenna, and so on and so forth. We do it for all the receive antennas. Similarly, at the rth receive antenna, what we have is we essentially have to remove the cyclic prefix, that is CP removal, followed by a serial to parallel demux. Alright, we have removal of the cyclic prefix followed by a serial to parallel demux, followed by, now we have the endpoint, we have the endpoint IFF, we have the endpoint FFT, and this is essentially performed at the rth receive antenna. This is essentially performed at the rth receive antenna. Now, remember, as we said, we have to perform MIMO detection, which means across each subcarrier we have to perform MIMO detection, and that has to be done for all the n subcarriers. Hence, what I do is, for the first subcarrier, alright, I take the output from the first transmit antenna. Similarly, I take the output across the first subcarrier from the second receive antenna. Similarly, I take the output from the first subcarrier across the rth receive antenna, and essentially what I will do is I will process all of these now as the MIMO detection. Alright, so what I am doing now is I am doing MIMO detection for the first subcarrier. Remember, each subcarrier is now a MIMO system. So, I will take from all receive antennas, I will collect the received symbols corresponding to the first subcarrier, and I will perform MIMO detection. Hence, this is the MIMO detection block for the first receive antenna. This is the MIMO detection block for the first receive antenna. Similarly, we can perform MIMO detection for the second receive antenna. Similarly, we can perform we have to perform MIMO detection for the second subcarrier, MIMO detection for the third subcarrier, and so on and so forth, MIMO detection for the nth subcarrier before multiplexing all these symbol stream. Due to lack of time, I will have to end the lecture here. We will continue from this point, complete this schematic, and proceed on to the next section in this. Right? Thank you very much.